Okay. Hello students. Good morning. Good morning. Am I audible? Please see, check whether I am audible or not. Reply in your chat box. Good morning, everyone. Units and dimensions. We were covering units and dimension. Okay, Sham. Very good. Very good. So units and dimension we were covering in the previous class. We have covered properties. We have covered applications of dimension in the last class. What are dimensions? Dimensions are the powers of derived quantity in terms of fundamental physical quantity. A derived quantity can be written in terms of fundamental physical quantities. The powers of fundamental physical quantities are called dimensions. The powers of fundamental physical quantities on which a physical quantity, derived physical quantity is dependent, that is called dimensions. For example, dimensions of force. Force was mLT minus 2. Dimension of force was mLT minus 2. This is the power. Here the power of mass is 1, the power of length is 1, the power of time is minus 2. These powers are the dimensions of force. Dimensions of force in terms of mass is 1, in terms of length 1, in terms of time minus 2. And in terms of other fundamental physical quantity, they are not present, so 0. There are total, we know there are total how many physical quantities which are fundamental? How many fundamental physical quantities we have in SI system? Tell me everyone. First of all, I am audible. Everyone is able to see me? Yes, Manish and reply, Manish Sham replying. Very good. Okay. So 7 fundamental physical quantities are there. Very good. You all are replying correctly. In SI system, there are 7 fundamental physical quantity. Plus 2 are supplementary or complementary. Plus 2 are supplementary or complementary. Fundamentals are 7 and 2 are supplementary or complementary. What are these two quantities? Angle and solid angle. Plane angle and solid angle. These two are supplementary. Why these 7 quantities are called fundamental? Why these 7 quantities are called fundamental? Because these 7 quantities cannot be derived, cannot be described, cannot be defined in terms of other. These 7 are independent of others. Any one of the 7 can also be not described in terms of other 6. We cannot describe or derive any one of the 7 in terms of any other physical quantity. We cannot derive other 6 physical quantities. So every fundamental physical quantity is independent of other fundamental physical quantities. This is the main logic. Every fundamental physical quantity is independent of other fundamental physical quantity. Okay, so let me ask you a question. Which of these quantities cannot be derived in terms of mass, length and time? I am asking which of these quantities cannot be derived in terms of mass, length and time. My first option is momentum. Second is angular momentum. My third option is let's say Planck constant. And my fourth option is a coefficient of linear expansion. Coefficient of linear expansion. Temperature coefficient of linear expansion. Temperature coefficient of linear expansion is denoted by alpha, Planck constant by h, angular momentum by L vector, momentum by P vector. So I am asking which of this physical quantity cannot be described in terms of mass, length and time. Some are giving me correct answer. Very good. Very good. Very good. So why option 4 you are telling me? Why option 4 is correct? Many of you are telling me option 4 is correct. Why? Why? Why option 4? why can't you describe or derive coefficient of linear expansion, temperature coefficient of linear expansion in terms of these three? In terms of these three. Durga Prasad is replying me yes. Durga, very good. And others, please reply fast. Why I cannot define or derive dimensions not there for 4. Very good, very good, very good. Momentum, angular momentum, Planck constant, these three physical quantities, they all are derived in terms of mass, length and time. If their dimensions are in terms of mass, length and time, you should remember their dimensions. The dimensions are in terms of mass, length and time. But this temperature coefficient of linear expansion, that alpha is defined as delta L by L delta T. Delta T here is temperature. So I am writing that theta because T we can write it for time. So for temperature I am writing theta. Okay. So delta L by L will be dimensionless, change in length upon origin length. Temperature is there in denominator. So dimension of this will be K inverse, temperature inverse. So temperature, in terms of temperature, we have coefficient of linear expansion and temperature is not here. I cannot find temperature using these three because temperature is another fundamental physical quantity that cannot be derived in terms of mass, length and time. So correct answer of this question is fourth. And any other physical quantity which contain temperature, mole, current, any other thing other than these three, that also cannot be derived. Suppose I ask you, can mu naught be answer? Yes, mu naught is permeability of free space. Epsilon naught be an answer? Yes. Charge can be an answer? Yes. Electric field, magnetic field, all this kind of expressions, all this kind of quantities which contain either current or some other physical quantity like universal gas constant R. Universal gas constant contain mole. This is not also not here. So that also can be an answer. That also can be an answer. Any other physical quantity which have other fundamental physical quantity than these three, that also can be an answer. Is this understood? Any physical quantity which contains more than mass, length and time, that also cannot be derived only using mass, length and time. Okay, so we have done one example question today. Let us do one more example question. One more question. Which of these pairs or set of physical quantities cannot be a set of fundamental quantities? I am asking which of this set. I am going to give you sets of quantities and tell me which set cannot be a fundamental set. Which set cannot be a fundamental set? First set is force, time and speed. Second is momentum, force and length. Momentum, force and length. Third, momentum, force and length. Let me change this. I will change this option. Momentum, force and one option I will give you is velocity. One option I am giving you velocity. Third set is time, frequency and mass. Fourth option is temperature, mole and current. So my question is which of this pairs or set of physical quantities cannot be a set of fundamental quantity, cannot be a set of fundamental physical quantity? cannot be a set of fundamental physical quantities. What are fundamental physical quantities? Some are giving me the wrong answers. A set of fundamental physical quantities is a set in which any quantity is not dependent on any of the other. Any quantity cannot be described with help of the other. Kusuma, your answer is correct. Very good, Kusuma. Charita, your answer is also correct. Very good. All others are wrong. Charita, very good. Which of these sets of quantity? Pawan, good. Which of this set of quantities? Which of this set of quantities cannot be a set of fundamental quantity? A set of fundamental quantities. A set of fundamental quantities will be such that any of them cannot be derived in terms of other. Any of them cannot be derived in terms of other. Any of them cannot be derived in terms of other. If you see force, time and speed. Force, time and speed. Can I derive speed in terms of time and force? Can I derive speed in terms of time and force? No. I cannot derive because force contains mass, time is a fundamental physical quantity. So this speed cannot be derived only using these two. Or even I cannot derive force using only these two. Speed and time alone cannot give me force because time contains only t, speed contains only ln t, or force also contains mass mlt minus 2. So using these two, I cannot derive this. Using these two only, I cannot derive speed because these two will contain mass. And using force and speed, I cannot derive time. Using force and speed, I cannot derive time. So this is a set of fundamental quantities. This is a set of fundamental physical quantity. We cannot derive any one of them using other two. Similarly, for second option also, momentum. Momentum is mlt minus 1. Force, mlt minus 2. Using force and momentum, we can derive time. But time is not here. Velocity is there. Velocity is lt minus 1. I can use momentum and force, I can use momentum and velocity to derive mass. I can use momentum and velocity to derive mass. See, the ratio of this is mass. But again, this is also containing time to the power minus 2. So we alone, these two cannot give you force. Momentum and velocity cannot give you force. So this can be a set of fundamental quantity. But third option is not a set. Why this third is not a set? Time and frequency are just inverse of each other. Time and frequency are just inverse of each other. Frequency is just 1 upon time. Time is just 1 upon frequency. They can be derived from each other. So this third option is not a set of fundamental quantity. This is also a set of fundamental quantity. Temperature, it's actually a fundamental physical quantity. Mole, SI system, this has fundamental. Current is also fundamental. So they cannot derive from any of other. So only possible wrong answer here, which is not a set of fundamental physical quantities, 3. So we will choose option 3. Option 3. Is this clear? Option 3. Option 3 is a set which cannot be a set of fundamental because time and frequency can be derived from each other. Time and frequency can be derived from each other. Please check it. Okay, very good. Kusuma saying she is clear. Very good. Time and frequency, they can be derived from each other. A set of fundamental physical quantity, any one of them cannot be derived in terms of other. Okay. So we are doing some questions. Next question. Convert G, which is 6.67 into 10 power minus 11 Newton meter square per kilogram square into CGS. Convert value of G into CGS. Convert value of G into CGS. Convert value of G into CGS. Very good, Vijay. Value of G, you need to convert value of G into CGS. G is 6.67, 10 power minus 11. Newton meter square per kilogram square. Newton meter square per kilogram square. So we can convert every unit here into CGS. We can convert every unit here into CGS. That will give us value of G. 6.67 into 10 power minus 11. 1 Newton, convert this into CGS. 1 Newton, 10 power 5 dyne. 1 Newton, I can write 1 Newton is 10 power 5 dyne. Meter, I can write 100 centimeter. But there should be a power 2. Divided by kilogram. 1 kilogram is 1000 gram to the power 2. Now solve this expression. 6.67 into 10 power minus 11. 10 power 5. 10 power 4 will come from this expression. And division we will have 10 power 6 dyne centimeter square per gram square. What is this? If you solve the powers correctly, this is going to be 10 power minus 8 in CGS. This is the correct answer of G. 6.67 10 power minus 8. How I am converting this? I am converting every unit here into CGS. Okay, this is a quick way to convert units. Clear? So we are just doing some questions regarding dimensions, units and dimension. Okay, so next question. Next question. If energy equal to gravitational acceleration to the power P, Planck constant to the power Q, and speed of light to the power R. Find PQR. Find PQR. G is gravitational G is universal constant of gravitation. Universal constant of gravitation, not gravitational acceleration. Universal constant of gravitation. H is Planck constant. C is speed of light. C is speed of light. Find PQR. Find PQR. Find PQR. Find PQR. This is a little lengthy question. Find PQR. Find PQR. G is universal constant of gravitation. What is dimension of universal constant of gravitation? G is used in this formula. G F equal to G m1 m2 by r square. If you don't remember any dimension, derive this. So dimensions of G, that will be dimensions of Fr square upon m1 m2. Dimensions of G, dimensions of F mlt minus 2 into r square divided by mass square. So this is m power minus 1 L cube t power minus 2. Dimensions of G. Dimensions of Planck constant. Planck constant and angular momentum have same dimensions. Angular momentum which is mlt minus 1 into length. Momentum into length. So ml square t minus 1. C is speed of light. Speed of light. Speed of light. Speed has dimensions of lt minus 1. So what is the dimensions of LHS in this expression? LHS is dimensions of energy. Dimensions of energy is ml square t minus 2. Dimensions of energy. What is dimensions of RHS? Check the dimensions of RHS. So dimensions of RHS, that will be G. What is G? M minus 1 L cube t minus 2 power P. What is H? M S square t minus 1 power Q. C LT minus 1 power R. Arrange the powers. Arrange the powers. Power of M minus P here, then plus Q here, and last term does not have M. M to the power minus P, power minus 1 and power P. So minus P here, Q, so minus P plus Q. Total power of M is minus P plus Q. Length power 3P, 3 and P, then 2P, then here it is R. Time period to the power minus 2P, then minus Q, minus R, minus R, minus R. It should be minus R. Last term is minus R. Okay. So dimensions of LHS and RHS now we know. We can create equations using dimensions. If you compare power of M, power of m should be equal both sides. So minus p plus q should be equal to 1. This expression gives you 3p plus 2q plus r. Dimensions of L should equal to dimensions of L, that is 2. And compare the dimensions of time. Here the dimensions of time is minus 2p minus q minus r. That should be equal to dimension of time and energy, that is minus 2. It is minus 2. So by comparing these 3 dimensions, I am getting 3 equations. Now solve these 3 equations. Solve these 3 equations. So for solving equation, we should first observe equation. What are they telling you? The first equation is giving you relation of p and q. And second 2 equation also contain r. So if some way I can remove r from these equations, I can get another equation in terms of p and q. Then I can solve easily. So to remove r, if you see properly, there is plus and minus sign of r. If we add this two, r will get cancelled. If we add this two, r will get cancelled. R will get cancelled. Why I am thinking about r? Because my first equation is only in terms of p and q. So I can get another equation in p and q. That solution will become easy. So add this two. Plus r and minus r, 0. Plus 2 and minus 2 is also 0. Very good. 3p and minus 2p, p. 3 times p minus 2 times p, p. 2 times q minus 1 times q. So plus q. So I am getting p plus q equal to 0. From this equation, p plus q equal to 0. It means q is minus p. Q is minus p. Q equal to minus p. I can substitute that in the first equation. My first equation is telling me minus p plus q. Q is minus p. That is 1 minus 2p equal to 1. So p equal to minus 1 by 2. This is the value of p. Minus 1 by 2. By solving this equation, I am adding last 2 equation to eliminate r. By eliminating r, I am getting p plus q equal to 0. With p plus q 0, I am getting q equal to minus p. I am substituting that here. Minus 2p equal to 1. So value of p is now known to me. If p is known, q is also known. Because q is just negative of that, negative of p. It should be plus half. And if you put value of p and q, suppose in this equation, use this equation, put the values of p and q which we have obtained, minus 2 into p. What is p? Minus half. Minus q. What is q? Plus half. Minus r, that should be minus 2. Solve this. Take that r there, 2 here. So minus minus will become plus, 2 to 1, minus 1 by 2. Take that 2 on this side, r on that side. What is this? 2 plus 1, 3. 3 minus half, 5 by 2. This implies that r is 5 by 2. So these are my answers. Value of p, we already know value of p is 1 by 2. Value of q is 1 by 2. And value of r is 5 by 2. So in question, I am asking you, find the value of p, q, r. If energy is g to the power p, h to the power q, c to the power r, find values of p, q, r. So how we are calculating p, q, r? I am comparing dimensions of LHS and dimensions of RHS. By comparing dimensions, I am getting some equations of p, q, r. And solving this equation is maths. That is maths. Okay. So after solving this equation, I am getting p, q, and r. So if you see question like this tiny steps, by I am comparing dimensions of LHS and RHS, then I am getting 3 equations. I am solving equation. So by solving equation, I am getting PQR. So question will become very simple. If you will feel that question is very simple if you break the questions. Okay. If you break the question in 3 steps, comparing dimensions, getting equations, solving equation. Only 3 steps are involved. Please see. Are you able to understand everything? Is this question completely understood? Check. Is this completely understood? Sham is saying me correctly. Okay, very good. Everyone else, please see. Okay, very good. So everyone is telling me done. Very good. So we have done today some examples question. We have derived, we have done some questions. we have converted units, we have derived relationship of energy with these three other quantities. Okay, so all kind of application we have done some questions on that. Okay, now we will start our next point, next thing which we should learn, that is significant digits. Significant digits. So now we'll start significant digits. For that I will take help of, for significant digits I will take help of some text, because a lot of theory is there in significant digit. So I will take help of some text. Okay. See, this is our module. So till now we have covered units and dimensions. Till now we have covered units and dimension. Now we will start errors. And in errors, first point is significant figures. Significant figures. Significant figures or digits. Okay, significant figures or digit. Okay, I will explain everything. Okay, this text is only so for that we all the rules are already written, so it will be better for you to note. Okay, now if I ask you what is length of this pen, if anyone asks you to measure anything, we can measure. We can measure. Suppose I ask you what is length of this pen. So this is around 15 centimeter, or let's say it may be 14.2 centimeter. Let's say this kind of data we can get 14.2 centimeter. Suppose for example we are getting 14.2 centimeter. So this 14.2 we are getting from measurement. These three numbers 1, 4, 2, 14.2 we are getting from measurement, and these three are significant. Whatever numbers we are getting from measurement, those are significant, those are important digits. In this 14.2, last digit may be uncertain, because whenever we are measuring something, it's bound to, errors are bound to happen. There are some mistakes going to happen. So the last digit is always uncertain. So number of total digits which we are getting from measurement, or number of digits which we are certain about, and the last digit for which we are uncertain, the total number of digits is called significant digits. So significant figures or significant digits in a measurement are the numbers. Significant digits in a measurement are the numbers which you are getting by measurement. Which you are getting by measurement. Okay. Yes. So the significant figures or digits, significant figures or digits in a measurement are the figures or digits that we know with certainty, that are measured, that are known with certainty, plus one that is last one, that is uncertain. So significant figures in a measured value of physical quantity tells us the number of digits that we are sure about, we have confidence with. Okay. And if we are measuring any physical quantity with greater number of digits, that is measured with better precision. Suppose I measure this pen with help of some other kind of scale, suppose 1 year scale. So 1 year scale will give me one more digit. The reading of 1 year may be of the kind 14.23 centimeter, 14.23 centimeter. By scale I am maybe getting only 14.2. With help of 1 year I will getting one more digit. With help of a better scale I will get some more digits. So how many digits you are getting from measurement? If the number of digits is more, your precision or your accuracy is more. So greater is the number of significant digits, greater is the accuracy. Greater is the number of significant digits, greater is the accuracy. Now there are some rules to find out number of significant figures. We have set some rules to find out to decide total number of significant digits. First rule, all the non-zero digits are significant. In any measurement, whatever the digits you are getting which are non-zero, all those are significant. 1984 has 4 significant digits. If I ask you what is the total number of my fingers, you will reply 10. 10 has 2 significant digits. Whatever number you are getting from measurement, and if they are non-zero, they all are significant. All the zeros between two non-zero digits are significant. For example, this number 10806 has 5 significant digits. If I ask you what is the total number of let's say human being on earth, so that number, whatever number you are getting, in that number you may be getting zeros. If I ask you what is the total number of many examples I can give you, total number of apples in a container. Suppose a container contains 100 apple. So 100 is from measurement, those are significant. If the apple number is 102, so 0 which is included between two non-zero digit, that is also significant. Any 0 which is in between two non-zero digit, that is also significant. Number 1005, number 1005, this is I think not visible. Number 1005, this has 4 significant digits. Any zeros which are in between two non-zero digits are significant. Any 0 which are in between two non-zero digits are significant. Okay, rule number 2. Rule number 3. All the zeros to the left of first non-zero digits are not significant. Are not significant. This example has only 3 significant digits. But I can give you one more example. 0.000123. This example has many zeros, but zeros left of first non-zero digits are insignificant. These are not significant. This example contains only 3 significant digits. Is this clear? This third rule, we are talking about third rule. In third rule, the digits, the zeros before first non-zero digits, are all non-significant. They are not significant for us. Only 3 digits are significant. Is this rule clear? Ardhaminda, 0.00123 only has 3 significant digits. Fourth number rule. If the number is less than 1, then all the zeros after point, on zeros on the right of the decimal point, but to the left of first non-zero digits are non-significant. Any point which is right of decimal point, but for this example, the same example, this example has many zeros. So all the zeros which are left of, which are right of decimal, but left of first non-zero digits, they are not significant. Fifth rule. The trailing zeros to the right of last non-zero digits in a number with the decimal points are significant. Any zero which is after decimal points, and after a non-zero digit, that is significant. Okay, for example, 1.00 has 3 significant digits. 3. This 1, after 1, whatever zeros are coming in point decimal numbers, they are significant. If I write 0.1200, whatever zero is coming after the first non-zero digit, they are significant. This here 4 significant digit. If I write 0.00211320, again this number has 4 significant digits. 4. Why? These starting zeros are not significant, but after the non-zero digits, all zeros are significant. One more example, 0.010200300. Tell me how many significant digits are there in this number, in this last example? 7. Very good. This 0 before first non-zero digit, they are not significant, but after 0, 1, 2, 3, 4, 5, 6, 7. There are 7 non-zero digits here. These are significant. These 7s are significant. Any 0 after a non-zero digit are significant. Very good. Okay. So let us make some space. Till now we have covered rule number 5th. Okay, rule number 5th. Now let's go to rule number 6. Rule number 6. The trailing zeros in a number without a decimal point may not be significant. The trailing number without a decimal point may not be significant. Suppose I am getting a number like 100, only 100, in which there is no decimal point. This is a number, just a number I am getting. So these last two digits are not significant. It may not be significant. I'm telling you, may not be significant. Please see this line here. It may not be significant. In some situations, they are significant. In some situations, they are not significant. If this 100 is obtained with help of measurement, then these two digits are significant. If this 100 is not obtained with help of measurement, then this 100 only has one significant digit. Suppose I ask you, what is the total number of boys in a class of 100 boys? A class contains exactly 100 boys. And I ask you, what is the total number of boys? And you are counting number of boys and you are getting 100. So you are getting 100 by measurement. Then 100 contains three significant digits. Whatever zeros you are getting by measurement, those are significant. If this 100 is just a number, I am writing just a number, this is not by measurement, then this contains only one significant digit. But if I am getting this number by measurement, by counting or something, then this has three significant digits. Okay, this is a tricky point. Are you understanding this point? If the number is obtained with help of measurement, by measurement we are getting this number, then all the zeros are significant. 100 contains three digits, this 3 will be significant if all the zeros are obtained with help of measurement. But if we are just writing any number, 100, then that contains only one significant digit. Okay, very good. Next rule. Next rule. Sixth rule. The trailing zeros, this is we have covered. Seventh rule. Next is 7. When the number is expressed in exponential form, in exponent form, when I represent a number in power of 10, that number representation in that format doesn't change the number of significant digit. 12.3 can also be written as 1.23. I'm making point forward, so power of 10 should be increased. Whenever you make point forward, whenever you jump a point forward, power of 10 should increase. If you take this point backward, 123, then power of 10 should be decreased. Power of 10 should be decreased. All these three numbers has only three significant digits. By changing the power of 10, number of significant digits does not change. By changing the power of 10, number of significant digits does not change. Is this point clear? In exponent formats, if you change the power of 10 by jumping point, the number of significant digits should not change. Clear? Very good. Okay. So these are the rules of significant digits. How many rules we have covered? We have covered 7th rule. How many rules are there? 7. What are the rules? Let us go once again with these rules. Okay, let us revise these rules once again. The first rule was all the non-zero digits are significant in any measurement. Whatever number of digits I am getting by measurement, all are significant. In those, the zeros are also significant. All the non-zero digits are also significant. All the zeros between two non-zero digits are significant. All the zeros to left of first non-zero digits are not significant. 0.00108. This contains only three significant digits. If the number is less than 1, zeros on the right of decimal points, but to the left of first non-zero digit. To the left of first non-zero digit, but right on the decimal point, these are insignificant. 0.002308. This zero is significant, but these starting zeros are not significant. But after decimal, whatever after a non-zero digit, whatever zeros are coming, those are significant. So this number 1.080 has four significant digits. Okay, this is rule number 5. Rule number 6. All the trailing zero in a number without decimal may be significant. May not be significant. For example, 010100. this contains 3 digits only, has 3 significant digits. But if we are getting anything from measurement, then those all digits will be significant. So remember for rule number 6, if the zeros after a non-zero digits are from measurement, those will be significant. 7th rule, exponent changing the powers of 10 doesn't change the number of significant digit. Okay, so these are our rules of significant digit. If I add two numbers, I will get some new quantity. For example, if I am having 3 sides and they are creating a triangle, I am having 3 lengths and they are creating a triangle, and I ask you what is the perimeter of triangle. To find perimeter of triangle, you will add the 3 lengths. For finding perimeter of triangle, you will add the 3 sides. By adding, what will happen to number of significant digits? What are the rules of addition and subtraction in significant digits? So now we'll cover those things. Rules of arithmetic operations with significant figures. Rules of arithmetic operations with significant figures. If we are adding or subtracting, we should observe the number of significant digits after the decimal. Let us go back to our board. Suppose I am adding 12.0 with 1.12. I am adding 12.0 with a number 1.12. I am adding 12.0 with a number 1.12. So if you are adding two numbers, you should see the digits after decimal. After decimal, first number has only 1 digit. After decimal, second number has 2 digits. Add these two numbers, you will get 13.12 after addition. But we cannot report this answer. Why? Because after decimal, in one number, you have only 1 significant digit. So only there should be 1 significant digit after decimal. So this should be rounded off to 13.1. This should be rounded off to 13.1. Correct answer will be 13.1. Why 13.1? It is not because we are having 3 digits here. It's not because of that. It's because after decimal, we need to see how many number of digits are there. After decimal 1 here, after decimal 2 here, whatever is the least number of digits after decimal, that will be an answer. Okay, let me give you one more example. 10.00. If this is added with 123.456, I am adding this to number. I am adding this to number. First number has how many significant digits? 4. Second number has 1, 2, 3, 4, 5, 6. 6 significant digits. So I am adding 4 and 6. So answer will not contain 4. It is not rule like that. Okay. We will see the number of significant digits after decimal. After decimal, there are 2 digits here. After decimal, there are 3 digits here. So after decimal, there should only be 2. See the digits after decimal. So add these two, you will get 133.456. But after decimal, you should have only 2 because first number contain only 2 digits. So your answer should be 133.45. This should be your answer. We need to see the numbers after decimal. Sir, but after 12, we can keep so many zeros now. No. In this number, after 12, we cannot increase the number of zero because all the zeros after a non-zero digit, all the zeros after a non-zero digit are significant. So we cannot increase zeros by our own. Okay. We cannot increase 0 by our will after a non-zero digit. So if you are adding or subtracting, and subtraction also same rule will be followed. If you are adding or subtracting to number, see the number of digits after decimal. Whatever is the number of least digits after decimal, answer will contain that much number of digits. Answer will contain that much number of digits. So this was rule of addition. Rule of addition in significant digit. Now we will learn rule of multiplication or division. Rule of multiplication or division. Multiplication or division. In case of multiplication or division, rule is very simple. Just observe the total number of significant digits. Total number of significant digits in the two numbers. Suppose I am multiplying 12.1 with 1.0. Suppose I am multiplying 12.1 with 1.0. Just multiply the two number first. 1.0 is like 1. So if I multiply this, I will get 12.1. This I will get. This first number contains 3 significant digits. 3 significant figures. The second number contains 2 significant figures. So whatever is the least number of significant figures, those many will be in your answer. So change your answer to so that it contains only 2 significant figures. Change your answer so that it contains only 2 significant digits. So change your answer. For 2, remove this one. For 2, remove this one. So answer should be 2. Answer should be 12. This should be your answer. Okay. For multiplication or division, we should observe the number of significant digits, total number of significant digits. One more example. 14.0, let's say this is multiplied with 14.0 is multiplied with 1.4. I am multiplying 14.0 with 1.4. This 14.0 has 3 significant figures. 1.4 has 2 significant figures. So the answer will contain only 2 significant figures. Multiply this 14.4 into 1.4. 14 into 14. 14 into 14 is 196. 14 into 14 is 196. 196. But I should have point here. I should put a point here. So 19.6. 19.6. Now my answer should contain only 2 digits because this number is 3, this number is 2. Least number of significant digits is 2. So my answer should contain only 2 digits. So round off this to 2. Now rules of rounding off should come in play. Rules of rounding off should come in play. If I am removing any number, which is greater than 5, then increase number before it by 1. So this can be rounded off. 19.6 can be rounded off to 20. My answer should be here 20. I am removing 6 now. It is greater than 5. If it is greater than 5, then answer should be 20. Suppose my answer, for example, suppose my answer was 19.1 and I need to round off it to 2 digits. So that will be only 19. Whatever digit I am leaving, if that is less than 5, make it as it is. If this is greater than 5, increase the number by 1. Is this clear? These are rules of rounding off. Okay, so what is rules of rounding off? Rules of rounding off. If the number which you are leaving, suppose you are leaving 12.4532 is there. I want only 2 digits after decimal. I want to round off it to 2 digits. So it should be 12.4532 I am leaving. This is less than 5. So leave it as it is. Okay. But if you have 13.2268. Suppose your number is 13.268. And suppose I want to round off to only 1 digit after decimal. 1 digit after decimal. So 13.2, because the rounding off number, you are leaving the number which is greater than 5. So increase this number by 1. So it should be 3. We should make it 3. Rounding off of this number into 1 digit after decimal is 13.3. Okay. So whatever digits we are leaving, observe those. If those are less than 5, leave it as it is. If these are greater than 5, increase a digit before by 1. But with case of exactly 5, suppose you are rounding off, let's say 12.5. I need to round off this to 2 significant figure. Suppose I need to round off this to 2 significant figure. I am going to leave 5. If I am leaving 5, I am removing 5 digit here. Then see the number before it. If this is even, leave it as it is. If this is even, leave is as it is. For even number, we will not do anything. But if this is odd, suppose we are rounding off 13.5, then odd we should increase by 1. So rounding off of 13.5 into 2 digits is 14. Because we are leaving 5, then this should be increased. Odd number should be we should make it even. Okay. So we have covered rules of rounding off, rules of significant digits in addition and subtraction, and as well as multiplication and division. So let us revise. For adding or subtracting, same type of rule is followed. Whatever is the number of digit after decimal, observe the number of digit after decimal, count the number of digit after decimal. Here first number contain only 1 digit, this contain 2 digit. So because this contain less number of digit, only 1, so the answer should also contain only 1 digit after decimal. Here also same example, you are getting 2 digits here, you are getting 3 digits here, so our answer should contain only 2 digits after decimal, only 2 digits after decimal. We should round off this 6 by rules of rounding off. By rules of rounding off, I should increase this number because I am leaving 6 here, so 4 5 I should increase it by 1, so correct answer should be 133.46 by rules of rounding off. I am leaving a number greater than 5 now, so I should increase this. Okay. In case of multiplication or division, rules is a bit simple. We observe the total number of significant digits. This and this multiplied, here 3 digits, here 2 digits, so answer should contain only 2. Whatever is the least number of digits, that will be an answer. Okay. This example, 3 digits, 2 digits, so answer will be 2. And whenever we are leaving some number, we are cutting off, truncating a number. So if the number here is greater than 5, we should increase this number. If the number is less than 5, we will leave it as it is. Okay, so these are rules of rounding off. 19.1, when rounded off to 2 digits, is 19. This rounded off to 4 digits, we are leaving 3 2, so 4 5. Less than 5, so it doesn't change anything. But if we are leaving numbers which are greater than 5, increase a digit by 1. Increase this last digit by 1. When we are rounding off exactly 0.5, then see the number. If this is even, leave it as it is. If this is odd, make it even. Okay? Are these rules clear? Are these rules clear? We have revised every rule again. Tell me. Okay. So we have covered rules of rounding off. Just a second. Where is our, just now we have covered, huh? This is finder now. So we have covered some rules of rounding off, rules of arithmetic operation with significant digits. Okay, and after that only one thing is now remained, which is scientific notation and order of magnitude. So we'll cover order of magnitude in the next class, and you can solve some questions from your gym book. This is your gym book, so solve this question. In the rounding off, we have also covered this. Okay, in the next class we will cover order of magnitude and do some practice question. Okay, after that we will cover accuracy and precision and errors. Okay, so I will leave it here. Revise everything and practice. Okay, thank you all of you. Best of luck for your test. Thank you.